Welcome to Lyons Township High School AP Physics. Today we got an example involving circular motion and specifically a car or roller coaster going through loop-de-loop. So you might want to pause the video and copy this down and write down the data. So give you a second to do that. All right, we're back. So here's what you're given. You're given you can either focus on the passenger or the coaster, it doesn't matter. We'll call that M. We'll say that the radius of the teardrop is 10 meters. Now when we say that, the radius changes throughout the teardrop. So we call this the radius of curvature. So at this moment, it's as if he's going in a circle that has a radius of 10 meters, which is 20-something feet. And we'll say at that moment he's going at a velocity of 20 meters per second. And we're going to find three things. We're going to find what's the normal force acting on the roller coaster or the person in terms of their mass. So we won't get an actual number, we'll get some number times m. How many g's does the passenger experience at this velocity? And then what's the minimum velocity required for that person to make it around the loop without falling out of the roller coaster, which should be less than 20, okay? And like with most of our problems, we'll do this with just variables, and then we'll throw the numbers in at the very end. Okay, so first off, what's Fn? Well, like every good problem, it's going to start with an FBD. All right. So what forces act? And I guess for this moment, we'll focus on the passenger themselves. So what forces act on the passenger? Well, this is pretty simple. You've got gravity, which is mg. Okay. And the only other thing that's applying a force to the passenger is the bottom of the seat. The seat is pushing on their derriere. Now, which way is that seat pushing on their derriere if they're making the loop and negotiating the turn without falling out? Well, they are upside down and the chair is pushing down on them. So the normal force from the chair also points down, and that's a key, okay? Now, for anything going in circular motion, we always split up forces into parallel and perpendicular to the motion. Both these forces are perpendicular to the motion. At this moment, he's moving left. These two forces point down. For circular motion, that perpendicular direction, we call that the radial direction. And you always call toward the center of the circle is positive, okay? There's always a radial acceleration toward the center of the circle. So at this moment, toward the center of the circle is down. So we kind of call that positive. I'll mark that in my diagram. Okay. And then we just apply Newton's second law to this. So we got net force in the radial direction equals MAR. These two forces are both pointing in that positive direction. So Fn plus mg equals m. And then A, for anything going in a circle, the radial acceleration is v squared over r. And then you've got an expression for Fn. If you subtract mg from both sides, you get m v squared over r minus mg. And then we can plug numbers in a moment, but I just wanted to make a note. So Fn is, going to be this minus this. If you're at the bottom of the loop, just as an aside, then Fn would point up, and up would be positive. And so this equation would change. You would say up is positive, Fn would point positive, and you would say Fn minus mg equals this, and then Fn would be this plus mg. So, and I'm sure if you've ridden a ride like this before, you always feel more pressure down here than you do up there. You feel heavier down here than you do up there, and this is the physics of why you do that. Now, as far as our numbers goes, okay, so we'll plug them in. So we got Fn equals m, v is 20, got to square that, over r, which is 10, minus m, and then g is 9.8. And we got some nice numbers here. 20 squared is 400, over 10 is 40. So we got 40m minus 9.8m, which is 30.2 m newtons. Okay, so that would be the amount of force that passenger would feel. So for instance, if you put, let's say a 60 kilogram passenger in there, they'd feel about 1,800 newtons of force acting on their derriere. Okay. Now, The next question we ask is how many G's does a passenger feel? Well, that's really simple. How many G's they feel is simply a ratio of the force that they feel versus their weight. Okay? So G's, in this case, what force do they feel? What force is acting on their body? Well, that's Fn. So it's going to be Fn over Fg, which for us is 30.2 m over 9.8 m. Now the m's drop out. And that's your G's you feel. So you feel just over 3 G's. I think I plugged it in and got 3.1. So 3.1 G's, okay? So what that means is that passenger feels 3 times their body weight acting on their butt. They feel 3 times as heavy. So somebody like me, I weigh about 175. So if I were in this ride, I'd feel 3 times that, which is whatever, 525 or whatever, of pounds of force acting on me. And that'd be uncomfortable, but that's not out of the realm of possibility for amusement park rides. They max out at usually 3 or 4 G's. Now, the last question we asked was, what's the minimum velocity you can go and still negotiate the turn? Okay, so it's going to be a lot less than 20 meters per second. Well, the good news is not much here changes. This is still your FBD, and this is still your math. Okay, the only difference is, if you're going the absolute minimum speed around that turn, Fn is getting smaller and smaller, and at the absolute minimum speed, Fn drops to 0. You're just getting ready to lose contact with that seat. That means that Fn is roughly 0. The force between you and the seat is becoming 0. So, at min velocity, Fn drops to 0. Okay? So in our equation right here, you can just start with this and you just set Fn equal to 0. Okay? So we have 0 equals mv squared over r minus mg. You move the mg to the other side, and you can, the m's drop out, and you get something like this. You get v squared over r equals g, or v equals root g r. Okay? Now, before we plug numbers in, something to note, mass dropped out. It doesn't matter if it's a little kid or a grown-up, the same min speed. So if you're the engineer designing that roller coaster, you do not have to worry about the passengers or the roller coaster's mass for that matter. Okay? Now, if we plug numbers in here, just for the sake of argument, we get 9.8 times 10, and that's going to be root 98, which is really close to 9.9 meters per second. So that's about half the speed we were going before. Okay, so if you're going that speed or more, you'll make it around the turn without falling out. If you go slower than that speed, then you got problems. All right, if you're not strapped into the roller coaster, if you're going slower than that speed, you would actually begin to fall out of the roller coaster in a projectile path as the roller coaster continued along the track, assuming that the roller coaster is actually attached to the track somehow. So that wouldn't be good. All right, so they make sure you're going at least that fast so that you don't fall out. Okay. Something to note here, since the normal force is 0, you would feel 0 G's, which means you would feel weightless. There are rides that do that on purpose. You get a similar thing when you ride, let's say, the Raging Bull at Great America, and you're going over the top of a loop. They make it so the normal force is roughly equal to 0, and you feel weightless. Now, I will make one more note. Even though the amount of G's that you experience is 0 G's, meaning you feel 0 G's, you are accelerating. Your acceleration is equal to G. So you have 1 G of acceleration, but you feel 0 G's because there is 0 normal force acting on you. So, hope that was helpful, and thank you very much. Oh, one more thing. Don't forget, physics makes you tough. Have a good one.